Welcome to our chemistry lecture on single and double replacement reactions. For those of you that are in my class, this is Unit 6. And thank you for watching. Let's get started. The questions we're going to be asking today: how can we determine the reactivity of elements? Today's objectives: we are going to predict the products and write a balanced equation for single and double replacement reactions, use the activity series to determine if the reaction occurs in single replacement reactions, and use the solubility chart to determine which, if any, of the products in a double replacement reaction is a precipitate. Now, some of those words might not make sense to you, but by the time we get through this lecture, everything will be okay. First, we will learn about single replacement reactions. There are four main types of single replacement reactions. You must use the activity series to predict whether a reaction occurs. Now, if you're in my class, you should have received this handout. Otherwise, you can just Google image search for activity series. Or you can take a screenshot of this slide. So here we have the activity series of metals. Be sure to note that only the metals above hydrogen are able to react with acids to form hydrogen gas. In addition, on this chart, the top four metals are the only ones that react with water. So if you're in my class, you did a lab where we saw the replacement of some of these metals with other metals, and some of them did not react. That is because those metals that are above the metals below them can replace them. However, if the metal is below, it cannot replace a metal that is above it. For example, copper cannot replace magnesium in a compound when magnesium's in a compound, say magnesium oxide. The four types of single replacement reactions: metals replacing other metals in a compound, which you did in the lab; metals replacing hydrogen in an acid, which we also saw in lab; the third type, nonmetals replacing other nonmetals in a compound; and finally, metals replaced in water by producing a base, which always ends in OH, and hydrogen gas. Notice here that types 1 and 3 are like replacing like. So only metals can replace other metals. Nonmetals can't kick out not other metals, but they can kick out nonmetals like themselves. And also remember that hydrogen can sometimes act as a metal. Let's look at a couple of examples. First, we have magnesium reacting with lithium nitrate. We have to check our activity series to see if there is going to be a reaction. And we can see from our activity series that lithium is above magnesium in the activity series, therefore there's no reaction. Magnesium cannot replace lithium because lithium is more active than magnesium. Another example, tin chloride reacting with sodium. If you check your activity series, let's see if there's a reaction. And there is absolutely. Sodium is higher than tin on the activity series, so therefore it replaces sodium. Sodium replaces tin in the reaction, producing sodium chloride and solid tin metal. The second type, metals replacing hydrogen in an acid. First example, zinc reacting with sulfuric acid. In these reactions, you're always going to have a reaction, so you don't have to check. Well, I take that back. You have to check your activity series to make sure that it's above hydrogen. Most of the metals are above hydrogen with the exception of a few. So zinc is above hydrogen on the activity series, and it can replace and form the hydrogen gas and zinc sulfate. The third type, metals replacing other nonmetals in a compound. First example, chlorine reacting with sodium bromide. Now you also have there's also an activity series for nonmetals. Thus, you have to check that, and from the activity series, you can see that chlorine is above bromine. So there's a reaction producing salt and bromine liquid. Remember our Hunkelbriefs, our diatomic molecules? Bromine is one of those. So make sure you balance the equation once you have determined what the products are going to be. Another example of nonmetals replacing other nonmetals, iodine reacting with calcium fluoride. What is our nonmetal in this case in the compound? It is fluoride. Fluoride is above iodine on the activity series, and there is no reaction. As I've mentioned already, remember that metals kick out other metals in a compound, and nonmetals kick out other nonmetals. The final type of single replacement reactions, metals placed in water produce a base, always ending in OH, and hydrogen gas. On the activity series, only the top 5 react with water. Those are the elements that we may have talked about need to be stored under a layer of oil because they're so reactive with water, they will even react with the water in the air to form a base and hydrogen gas. So they have to be stored under an inert substance like an oil so that that reaction doesn't occur. Sodium reacts with water. Sodium is one of the top 5 in the activity series, so it does react with water, producing sodium hydroxide and hydrogen gas. Take a moment to pause the video, take out a piece of notebook paper, and practice these problems. And when we come back, we will check our answers and move on to the other types of replacement reactions, the double replacement reactions. Welcome back. I hope you paused your video and have worked these out on your notebook paper or any scrap paper you have lying around. So first, let's look at chlorine and potassium iodide reacting together. We do have a reaction because chlorine is above iodine in the activity series. And we do need to add in a couple of coefficients to balance the equation. Second one, we also have a reaction because aluminum is above copper in the activity series, thus it can replace it, forming aqueous aluminum sulfate and copper solid metal. You notice there are no coefficients added. That's because this equation is balanced as it is. Next, we have potassium in water. Potassium is one of the top 5 elements, thus it is able to react with water, and we have to add in some coefficients to balance it out. And finally, tin and sodium nitrate. There is no reaction because tin is well below sodium in the activity series. Let's take a look at what happens when sodium reacts with water.
This will be a good one. Oh, that's sodium, dude. That's a little bit of sodium over there. Holy cow.
Excellent. So we have, you can see in this still at the end, the hydrogen gas being released. Now let's move on and talk about double replacement reactions. In double replacement reactions, you're always going to mix 2 aqueous solutions together, and you might get a precipitate. The 2 metals on the reactant side will just switch partners. You'll use the solubility table that is part of your handout on the activity series to predict if there is a precipitant. So sometimes you'll get it'll stay in an aqueous solution, and sometimes it'll be insoluble and will actually precipitate out. For example, if calcium carbonate is a product of a reaction, will it precipitate out? Check the solubility table on your handout, and you will see whether or not calcium carbonate is insoluble or soluble. Here's a little example, real world example maybe. We have the second hottest guy in school dating the second hottest girl in school, while the hottest guy in school dates the hottest girl in school. However, their interests don't really seem to line up, and they find that they might be happier if they switch partners. Let's go through a couple of examples. Hydrochloric acid reacts with silver nitrate. We know there's going to be a reaction because there's always going to be a reaction in double replacement reactions, but what are the products? What are our metals and what are our nonmetals? We have to check and see if they're soluble or insoluble when we determine what our products are. So the overall reaction looks like this. So hydrochloric acid and silver nitrate produce silver chloride and nitric acid. So you see in this case the hydrogen is acting as a metal, so it can replace silver in the other compound, and they just trade partners. If you look at the solubility table, it will tell you that silver chloride is insoluble, thus it is a solid precipitate. One more example. Potassium hydroxide reacting with phosphoric acid. The overall equation, 3 equivalents of potassium hydroxide react with phosphoric acid to produce potassium phosphate and water. Now we know what water is always a liquid, and we did double check that potassium phosphate is soluble, and so it is aqueous. This is a special type of double replacement reaction. When a base reacts with an acid, you will always get a salt and water produced. So your salt here is the potassium phosphate, and as you know, H2O is water. Take another moment to pause the video and practice these on a piece of scrap paper, a piece of notebook paper, and we will be right back to check our answers. Welcome back. I hope you had time to work out these problems and do a little do-si-do with your metals in the compound. So our first example, we do have a precipitate in the barium carbonate, so we have checked our solubility table to find that it is insoluble, so it is a solid precipitate. Our second example, we have aqueous sodium chloride, which you may know as table salt, and solid iron 3 phosphate that precipitates out. And finally, we have hydrochloric acid and sodium hydroxide. So we have an acid and a base. What do we get when we put an acid and a base together? We always get a salt and water. So again, we have NaCl, sodium chloride is a salt, and water is a liquid. That's all I have for you today. Thank you for watching. If you are one of my students, thank you very much for watching, and we will do lots of practice problems on these in class.